Okay, welcome everyone to the regression in Python, or actually regression techniques in Python, which is intermediate Python. This is the ASRI Summer 2025 workshop. And so this time we're going to be talking about regression. So different kinds of machine learning models that you can have. You know, when you're talking about models, you have classification models, you have regression models, and then there are even more interesting things like reinforcement learning types of models and those sorts of things. We're looking at regression here. I think there's another workshop for classification, and then there's another workshop for clustering that I'm doing. And so you're all welcome to join those too if you like. But if you're here, hopefully that means that your project or the thing you're working on has something that looks like a regression problem in it. And so we'll talk a little bit about what that is. And again, as we go along, I'm dropping in the chat a link so that you can open this notebook. And so please click on that link and open the notebook and follow along. We have a lot of time in here, so I'm going to go through this notebook sort of together. And so I would like you to go through at the same time that I do and run the cells and look at the code and see what the output looks like. And then we're going to cover quite a bit of ground, but I think we have enough time to do it. And so feel free to ask questions as we go along. This being an intermediate Python workshop, we do assume that you know a little bit about Python already. And so feel free to ask questions. If there's a question that's something that's essentially, if it's a how do we use Python question, I might have to move past it, and I apologize for that. But I'm happy to answer questions that are about, what are these models doing? Why did I do this with pandas, or why does my data set look this way? I'm happy to answer those questions as we go. And at the end, I think we'll have time left over to answer even more questions and maybe even questions about your specific projects. And so stay tuned for that. And I'm going to put that link into the chat one more time. And so again, feel free to bring that up. I left a few places in this notebook where there's a to-do, and so you'll have to actually stop and type something. Don't let that scare you. I'll be typing it right along with you. And I think there's only 3 or 4 of those, just enough to make sure that everyone's still awake. But the cells do need to be run as we go through the notebook. And so you'll get a chance to run the cells and see what they do. And so this notebook, it's using a few modules. And so I'm keeping it pretty simple here. I'm sticking to matplotlib, which is what does the graphing and charting, together with Seaborn to make some of the graphs look a little nicer. I'm using NumPy, which lets me do vector and array math. I'm using the pandas library, which gives you data frames. And I think you've probably already been doing these in your other Python workshops. They're pretty common. And I'm also using sklearn, or the scikit-learn library, so that we can use some machine learning and data manipulation from that library. It provides almost everything that you would need short of deep learning. And so as long as you're not doing deep neural network type stuff, sklearn can get you there. And it also is really good for experimental design, for doing cross validations, or training and testing splits. And we'll see a little bit of that as we go along. And so it's a nice one to use. And so actually it's not a lot of libraries. I'm using only a few things, but you can get a lot done there. So first of all, I wanted to just define a few terms and definitions. And I want to do this just so that I make sure that you guys know the words I'm using. So first of all, regression, if you're not sure what that means, as opposed to something like classification, regression is the process of predicting a continuous variable, meaning it's a number that could be any number. And so you're not trying to put things in groups, you're trying to give a number, an outcome. And that could be something like the price of a house. So maybe you're trying to predict housing prices, or maybe you're trying to predict the river level tomorrow, given some information about today. In our case, we're going to be predicting the miles per gallon of different kinds of cars based on information about the cars. And so it's predicting a continuous value given the random variables. And when I say random variable, what I mean is these are your inputs. So sometimes we call them input variables. Sometimes we call those features. Sometimes we call them measurements. And so that's just the things that you've gone out and measured that you're trying to use to make this prediction. So the Continuous, when I say continuous again, that means it can take on any value within a range. And so usually you think about these things as being floating point numbers, so things with a decimal point in them, although they could look like integers as well. So it could just look like a whole number. If I say the word sample, that just means one set of measurements. So I've gone out and I've measured one thing. In our case, we're going to be talking about cars. And so a sample will be information for one particular kind of car. And then I like this, how do you know if you have a regression problem? Well, you have a regression problem if the dependent variable, which is your output, is continuous. All right, so pretty simple. And if you're doing classification, you have a classification problem if the thing you're trying to predict is a class or a group. And so when we get started here, we're also going to look at regression problems where the random variables are continuous as well, just because it makes it a little easier. At the end of the notebook, I have some code that I will explain to you how to deal with categorical variables, which means variables that are not numbers. So they're strings or they're, object types or things that are true and false, things like that. And so, okay, let's look at a little bit of code. So we're going to work our way through here. And so this is the first point where we're going to run something. And so on this first cell, if you press the run button on there, it's okay. So it gives you a warning. It says this notebook was not authored by Google. Okay, so say run anyway. I'm not going to give you any viruses. So you run the thing and it should happen pretty fast. And so it's just going to run this cell, which is importing a bunch of things. And so you'll see I'm importing matplotlib, numpy, pandas, seaborn, and then I'm importing a whole bunch of things from scikit-learn. And I'm not going to talk about what each of those things are right now, but we will get to them as we go through the notebook. And so for now, it's just important that you run it and that it works. By the way, as we go through and run these cells, if something happens and it doesn't work for you, feel free to just please, you can unmute yourself and speak up, or you can put something in the chat. I do have the chat kind of in front of me. I think if you raise your hand, I may or may not see it because that's pretty small on a screen up in front of me. So feel free to just unmute yourself and ask, or put something in the chat and say, hey, this didn't work. All right, so let me tell you a little about the data set. I'm using a data set from the UCI Machine Learning Library, which is a good place to find practice data sets. And so the particular name of this data set, they call it Auto MPG. So you're predicting miles per gallon for different kinds of cars. And it's a pretty simple data set. It's big enough that you can do some interesting things with it, but it's not so big that you have to worry about, waiting for the thing to download or something. So it's something that's easy to work with, but big enough that you can do interesting things. All right, so now let's look at the data set. So this gets us to this column with some text in here. And again, we're going to run this one, and when we run it, it's probably going to do a download. Now mine, I ran this earlier, and so it's already there, but it should happen pretty quickly. So it's going to get a file. So this wget is just how, basically from the command line, I can download something from a website. And so I'm downloading from their link, and then I'm going to read that. So it comes in as a file with a weird name. It comes in as a file called autompg.data. That .data file is, they picked a name for it. It's really sort of like a CSV, except it's not comma separated, it's space separated. And so this actually is a more complicated than usual loading statement for pandas. So a lot of our data is real CSV, which means the numbers or the values are separated by commas. Well, in this case, if you open that file up in a text editor and look at it, you'll see that the data is separated by some amount of white space. And so pandas can handle that, but I have to do a little work. And so this middle argument here that says sep equals, and then so this R means regular expression, and then this regular expression means, so that \s means white space. It means some kind of white space. And the plus means one or more of those. And so any amount of white space is basically what that says. So a separator is any amount of white space. And then I'm also setting my column names myself because the data set doesn't have column names built into the file. And so I'm setting those column names here. And so I have my column names there, and I'm just telling pandas about the column names. And so when I load that up, I'm going to show the first few rows by using the head function on my data frame. And again, I think you've been using pandas already, so this should be unsurprising. And so you see those first 5 rows. And this is a good time, when you're loading data up, like you said, cleaning the data and making sure everything looks right is very important. And that can be very time consuming. And so this is our first look. We get to look at it and we get to say, does this look reasonable? And the good news about this data set is it's pretty clean. And so again, once you know that it is white space separated, the hardest part's probably figuring that out. And again, how would you know? Open the file in a text editor and just look at it. Right? That's the best way. And so we've looked at it, we've loaded it up. It seems to be loading correctly. And so I see my column names there. I see that these numbers look like numbers, and I see that the car name looks like strings. So there's letters, so different kinds of cars. So far everything looks okay to me. The origin column is just a number, but that number represents a place that the car came from. And there's more information if you go into the other information at the UCI repository. If the page for this data set, they tell you about those different origins. But that's what we have here. And the MPG, the miles per gallon column, is the thing I want to predict. And so right now I have it in there. Eventually I'm going to separate that out. And so we have the predictors, which is everything else. And then we have the target variable, which is MPG. And this is going to be supervised learning, by the way. So there's supervised and unsupervised learning. And the difference between the two is, do I know the answer already? And so if I know the answer, if I already know the output, I have supervised learning. And here I have the miles per gallon. And so I do have a supervised learning problem. And that's good to know because that determines what kind of models can I use and what kind of models can I not use. And most of your regression models are going to be supervised learning models. And so we're going to focus on that today. All right, so I'm going to do one more thing here just to make life a little easier. So I'm going to separate these things out by name. Pandas is really good about letting you select parts of your data frame by name, and it will let you supply lists of column names to select things. And so since I'm going to do that over and over, I don't want to keep retyping these names. And so I'm going to put these into Python variables. And so my target column is called MPG. And so I'm just going to put that into a variable. And my random variables are these others. And so cylinders, displacement, horsepower, weight, acceleration, and model year. You might notice I have left out car name. I mentioned, and I've also left out origin. So I mentioned earlier that I don't care so much right now about using categorical variables. And both origin, even though it is a number, it's acting as a label. So it's acting as place number 1, place number 2, place number 3. So it's not a measurement of something. It's a name. It's a categorical assignment of where the car came from. And then the car name is not all that interesting to me either at the moment, because again, it's a string, it's not a number, and I'm going to focus on things that are just continuous variables for now. We'll come back to that at the end. All right. So here are my predictors. So I have 6 of them, and I have 1 target variable. So let's not forget to run that cell. Okay, so the next thing I want to do is, again, looking at the data to make sure I have what I think I have and that everything's okay. So I'm going to call the info method from pandas. And this is a to-do cell, so I have to type some code, right? So this, please everyone do this with me. So make sure you run all the cells above you. And then when we do this to-do section here, we're going to enter this code. And the name of my data frame, by the way, this happened up earlier. It's called auto_mpg. That's my data frame's name. And so you do need to know that here. And so auto_mpg. And what I want to do is I want to call the info method. And since we're in a notebook, I can just run the cell and it will show it to me. If this was a regular Python script, I would wrap a print statement around that, but I don't need to do that here. So if you'll type in what I have there, so auto underscore mpg dot info, and then you should be able to run the cell. And you can do that by clicking on the run button there, or by just hitting command enter or command return or control enter if you're on a Windows machine. And you should see something that looks like this table that printed out on my screen. Again, this is a good moment for try it out. If it doesn't work, please let me know. All good? Did that work for everyone? Good deal. Okay, awesome. Okay, while everyone's trying to get that to run, I want you to look at what we see. So I have the column names, and so it's showing me the column names for all these different things. And it's also showing me the count. So how many non-null means how many not missing values do I have? And so it says 398 for all of them. And so that's good news. The fact that they all match, it means that they all have data. The data type there is shown as float 64. So float just means a thing that looks like a number with a decimal point. And the 64 is related to how much memory it takes. So I'm not worried so much about that. The int is a different kind of number. So cylinders is also a number, and it's just an integer number. And displacement is a number. So float 64. Same thing with weight and acceleration. The model year is a number. The origin, again, we're not actually using that as a predictor, but notice it did pick it up as an integer. And then the car name it picked up as an object. We said that that's actually a string. It's the name of the car. But the thing that worries me a little bit, look at horsepower. Now horsepower, if we look in our original table, horsepower looks like a number to me. Right? You would expect the horsepower, this first one is 130.0, so 130 horsepower. That should have been a float 64. But Pandas has detected it as an object. Now, when this happens, what that usually means, so object is sort of Panda's way of chickening out and saying, I don't think it's a number, so I'm not going to try to convert it. And I'm going to leave it in this object format, which really just means string. It's more or less interchangeable with a string in Pandas. And so now I know better. I know that that should have been a number. And so this means there's something wrong. And so just from looking at this info, I can tell that something didn't go perfectly. And so we've got to figure out what's wrong. So let's see if there's any non-numeric values. And so the most obvious way for Pandas to load something up that should have been a number and instead make it into a string would be for something in that column to not look like a number. And so what I've done here is I've written a little function to do that. Now I'll tell you, if I were doing this myself with not in a workshop, if I was just doing this myself, I probably wouldn't write this function to do it. What I would do is I would open that file up, the data file in my text editor, and I would just scroll and I would just look. Again, as long as it's a reasonable sized file, because that's faster than writing some code to do it usually, and you'll pretty quickly you'll see what the problem is. And so always do the easy thing. If you can open the data up and just look at it, that's probably what you want to do. But here, because we're in a workshop and the only way I have of easily showing things to you is to put it in this shared notebook, I've written a little function. And so this function is just figuring out if something can convert to a float or not. And so if it can, then everything works okay and it returns true. If it cannot, Python will generate this thing called a value error, and then I'll return false. And so this thing will give me a yes, no on whether things can convert to a number or not. And so what I'm going to do now is I'm going to take my data frame, AutoMPG, and I'm going to locate all of the horsepowers where when I apply this function, this isNumber function to the row, if it returns false, I want to show the horsepower, and then I'm going to count the values of all the different things. And so I want to know how many things are not numbers and what do they look like? What are they? And so that's kind of dense. There's a lot going on there, but I will be honest with you, in most cases, you don't need to do it this way because it's easier to just look at the data in a text editor. But when we run it, here's what we see. Well, there was only one thing that was showing up, but it occurred 6 times, and that was a question mark. So it looks like horsepower actually does have some missing values. It's just that they weren't omitted. Instead, they put a question mark instead of a number. And so from Panda's point of view, that made the whole column turn into object. And so that means we have to deal with it somehow. And so it's actually not so hard. What we can do, since we've only got one problem here, what I'm going to do is I'm going to read this data set again. So I'm just going to reread it as if I'm loading it up from scratch, because I've learned a new thing. I've learned that they're representing missing values, and so Pandas calls those NA values. It's representing missing values as question marks. And so I'm just going to reread the data frame. So all of this is exactly the same as it was before, but I've added this 4th argument, which is NA underscore values is set to a question mark. Everyone see that? And so that's going to cause it to load the data frame again, but it's going to do something different now. So every time it sees a question mark, it's going to make that into the numeric version of missing value. And so the info should look different. And so if we run this cell, well, now look at this. So now we have, okay, the good news, horsepower is set to float 64. That's exactly what we wanted. That's good. The bad news is we lost a few. So we know that there were 6. All right. So we know that there were some cases where there were question marks in there. And so we're down to 392 values for horsepower, whereas everything else has 398. So that means we have some missing values. How do we handle it? Well, the question of how you handle missing values in your data set is something we can come back to at the end if some of you have this problem. But the quick thing I'll tell you is if you only have a few, the most common way to deal with it is to drop the samples. So drop the rows that have missing values. If there's only a few, and in our case we only have 6, I think it's going to be okay. We have almost 400 samples. Dropping 6 of them is not going to make a huge difference in my data set. And so that's easy to do in Pandas. There's a function called drop NA that's going to drop those missing values. And again, remember Pandas calls them NA values. And so the way we're going to do this is we're going to call, again, so here's a to-do cell. So you are all going to be working along with me. So I've written some of the code for you. So auto MPG is assigned, auto MPG, and now we're going to start right here. So leave that code in place. And I'm going to start with a dot. And so what I want is the drop NA. And again, Google is nice enough, it's suggesting. So I'm going to use the drop NA method on that data frame. And normally, a lot of times it's enough just to say that, but I want to be specific about a couple of things. I want to make sure that I'm only looking at my random variable columns. And so there's a way to tell it that. So the subset we're looking at is random var calls. And remember, I've already put that in a variable, so I'm just going to say its name. And the axis that I want to drop is axis 0, which means dropping rows. So this means drop all the samples that have a missing value in any of the random variable columns. And so once you've typed that in, you should run it. Hopefully everything goes just fine and you get a check mark and everything's good. Okay. So if that worked out, what we have now is the next thing we're going to do is take a look at the data set. Again, looking at the data set, making sure it's clean. So we're going to visualize it using pair plot. And so this SNS, that's Seaborn. So I'm going to ask Seaborn to make a pair plot from my data frame, given the random variable columns, and I'm adding back in the target column. So only my random variables and my target. And then this corner equals true. That's just saying instead of showing me a big square that has duplicate information in the top and bottom triangles, only giving me the lower triangle. And you'll see what that looks like when we draw it. This takes a second. So go ahead and try to run that cell. And when it finishes, you should see something like what I have on the screen. And it's pretty big. Okay, it's pretty big. And so let me explain what we're seeing here. Out of curiosity, have you all learned to do pair plots in one of the other workshops yet? Amir says mine's not working. So which thing is not working?
So whenever it says basically have a name error, it says random var codes is not defined.
Okay. Scroll back up and make sure that you have run the cell that looks like the one on the screen. So see this cell?
Mm-hmm.
Make sure that you have run that cell.
Okay.
So go back up and hit the run button on it, and then go back down there and see if it fixes the problem.
I think it's okay, it worked. Okay.
All good?
Yeah, we're good.
All right, awesome. Okay. So has anyone used a pair plot, or is this new?
We did it earlier in the other class.
You did. Okay. So I'll be brief when I talk about it. So if you've used it, I'll just kind of review. And so with the pair plot showing along the diagonal, it's showing the distribution of each of the variables. So there's a question about drop rows with missing values. Yes. So that looks like this. Okay, and so for those of you who are looking at the pair plot, I'm going to leave this drop code on the screen for a second. For those of you who are looking at the pair plot, along that diagonal, you see the histogram, which is the distribution of each of the variables. And so, for example, if you were expecting your variables to have a normal distribution, then what you should see there is something that kind of looks like a bell curve. Yeah, it's taller in the middle and it's more or less symmetrical. You'll notice that a lot of our variables are not quite that, and that's not unusual. So it's not unusual in real data that you don't really have normal distributions, and so you have some other shape. And so the little labels are on the left-hand side and also on the bottom. And so this first column here represents cylinders. And cylinders is weird because it's an integer. You can't have half a cylinder. And so, it's 3, 4, 5, 6, and 8. And so that makes the plots look a little strange. And then the other plots have a lot more dots in there. And so what those scatter plots are showing you is when you compare one of the variables to the other. And so for instance, if you look at let's see, third row down, and then the second column there, that's weight compared to displacement. And so weight compared to displacement looks like a smear of dots, but they kind of go from the lower left to the upper right. And maybe there's even a little bit of a curve to that. So that's telling me that as the weight increases, so the weight is on the y-axis here, the displacement sort of increases, or you could say the other way around. The x-axis is displacement. As that increases, the weight also tends to increase. And so if I were curious about whether my variables were independent, this tells me they are not. So that's telling me that there's a correlation between displacement and weight. And so that's interesting. So again, some of your models might make some assumptions about that. Some of the other things we can see is there are actually lots of these cases where the scatter doesn't really look random. It seems to have a trend. It either goes up or goes down. And so that means that you have some kind of correlations between your variables. Those cases where it's a little bit more of a splatter and it's looks a little more random, that means you have less of a correlation. So those two variables are more independent of one another. So for example, acceleration versus weight is a little bit more independent. That still has a little bit of a pattern to it, but it's less than the others. The acceleration actually looks like the most normal of the variables. And then again, model year is not, so again, that's years, and years are kind of strange to look at. And so that one's a little weird. And then finally, the last one down there is miles per gallon. And so a couple things you'll see with miles per gallon. There is a relationship between several of these different variables in the miles per gallon. If we want to be predictive, that's good news. You want to see some relationship between your predictors and your outcome. And so at least it looks like displacement, horsepower, and weight are going to have some predictive value. Also, maybe cylinders. Acceleration, maybe less so. And model year actually has a trend. It's kind of a weird, fuzzy trend, but it does seem to go, from the lower left to the upper right a little bit. And so it seems like there's some good predictors here. All right, so the next thing I want to do is I want to investigate these correlations a bit more. Go ahead.
So I didn't clear about that pair plot. It shows the difference or comparison between the other variables.
It shows sort of like, it shows the relationship between them. So again, the diagonal is just the variable with itself. And so the diagonal is showing you the number of each value you received. And so the histogram, or you could think of this as kind of the empirical probability distribution of the different values. The plots that have the dots in them are showing you one of the variables on the y-axis and another variable on the x-axis. And so it's easier if I scroll down to the bottom. So this bottom row is miles per gallon. And so the y-axis is miles per gallon for everything on the bottom row. The x-axis is determined by these labels at the bottom here. And so for instance, the first one is cylinders, but that one's kind of weird. So the second one here is displacement. And so if you see that, it kind of goes from the upper left to the lower right. So it's a downward trend, and it's got a little bit of a curve to it. And so that's telling me that as miles per gallon, or as displacement gets bigger, so it kind of varies between a little less than 100 to maybe 500. As displacement gets bigger, the miles per gallon seems to go down. Does that make sense? And so we're seeing a relationship between those two variables, if there is one. In this case, it looks like there is. And that it also makes sense. So displacement means how big is your engine, basically. And so as the displacement gets bigger, as the engine gets bigger, your fuel mileage is going down. And that sort of makes sense. That's what we would intuitively kind of expect. Bigger engines are probably less fuel efficient. Did that answer your question?
Yeah, thank you.
Thank you. Good questions. And again, feel free to ask. Okay. So the next thing I'm going to calculate, so this is another visualization. This one's called a correlation matrix. And so I'm going to first do a correlation computation. And so I'm going to get the matrix itself, which is just a bunch of numbers. And those numbers might be interesting to you in a statistical analysis. But again, I'm not going to go deeper into it here. I'm just going to use these numbers to make a plot, and we'll talk about what they mean. And so again, I'm going to take my data set, my data frame, and I'm going to get the columns that I'm interested in. So I'm going to get the random variables, and also I'm throwing the target in there. So I'm putting those together. And then I'm calling the core method, CORR, which calculates the correlation. Now, up here in the scatter plot, we had some nonlinear relationships. So some of these variables, the relationship has a curve to it. The default kind of correlation most people do is called Pearson. And Pearson correlation suffers a little bit when you have nonlinear relationships. And so there is another kind of correlation you can do called Spearman correlation. And Pandas supports it, but you have to tell it. And so I'm asking for Spearman correlation here. And so again, a nice thing to know, just to kind of put that in your pocket, if you have a data set that's showing these nonlinear relationships, you might prefer Spearman correlation as opposed to the default, which is usually Pearson. And so that's going to give me this correlation matrix, which I'm then going to plot using something called a heat map, which just means draw squares that are different colors according to how big the number is. And so if we run it, we'll see that. And so we see this correlation matrix. I'm going to shrink that a little so we can see the whole thing. Okay, there's a lot going on here. You can see the numbers. So in the middle of those cells, you can see the numbers. You can also, on the right-hand side, there's a color bar that shows you the intensity of the colors. And so bright red means +1, and dark blue means -1, even though it's not showing up on the color bar there. And then right in the middle, there's kind of a gray area that means 0. And so the correlation, the way you interpret this is the closer a correlation gets to 1 or -1, the stronger it is. And then the sign tells you direction. And so a positive correlation means as one variable tends to increase, the other one also tends to increase. A negative correlation says they tend to go in opposite ways. So if one of them increases, the other one tends to decrease. By the way, that's a correct, good answer in the chat. So the difference between Spearman and Pearson correlation, essentially Spearman's for nonlinear correlations, or it's at least more robust for nonlinear correlations, and Pearson assumes linearity. If you get into the weeds about the math, essentially they're doing it, they're looking at the problem differently. And so Spearman is just doing a different mathematical trick to calculate the correlation than what Pearson does. And so it's less damaged by nonlinear relationships. All right. So on our chart, first of all, anytime you look at a correlation matrix, the diagonal is always going to be 1.0 because every variable is perfectly correlated with itself. And then again, this thing is symmetric about the diagonal. And so sometimes you'll see these things also shaped like a triangle where you only see half of it. So again, each row and each column represent a variable. And so we can see that cylinders is very highly correlated in a positive direction with displacement and with horsepower and with weight. And so all those things are very positively correlated with one another. There's also some things that are negatively correlated. So for instance, you'll notice that, as we said before, displacement tends to be negatively correlated with miles per gallon. Horsepower, if we come over here to the right, horsepower is also very negatively correlated with miles per gallon. Weight is negatively correlated with miles per gallon. And those kind of make sense when you think about it. A heavy car is probably going to get worse mileage than a light car. And there's a few that are pretty weak. And so some of these numbers like the 0.28, that's a pretty weak correlation. There's a negative 0.28. That's a pretty weak correlation. That just indicates that there's less of a relationship between those variables. Now, when I'm looking at this correlation matrix, there's different meanings depending on what you're trying to do. Some models make assumptions about independence of your variables. In particular, linear models tend to make some pretty strong assumptions about the variables, the predictors being independent. You can see very quickly here, we don't have a lot of independent predictors. There's tons of correlation in there. And so if I was going to use a linear model, I might be a little bit worried about that. Now, let me put a disclaimer in here. For the rest of this workshop, I'm going to ignore that. So it's there. It's probably going to cause a problem for linear models. I'm going to use linear models anyway, and we're just going to go on about our business. But it probably means that I should do some extra work. If I want to use a linear model, I should probably do something like a PCA transformation to get rid of those correlations. Okay? And you may have talked about that somewhere else. If not, we could maybe talk about that at the end. Now, the place where you do want to see correlations is between the predictors and the target. And so seeing some big numbers between some of the predictors and the MPG is good. And so I see they tend to be big negative numbers there, but that's, a big negative number is just fine. So it does seem that we have some pretty strong predictors of miles per gallon. And so that's good news. That tells me that we're likely to be at least somewhat successful predicting miles per gallon from this set of variables. Okay. And again, the text there kind of says some of that too, and so you can feel free to read along. So let's see. So, okay, we finally get around to doing a model. Let's talk about how we can actually predict. So these regression models, the simplest thing you could possibly do is to try to fit a line to your data, right? So a linear regression model just tries to fit a line. So as your predictor goes up, then either your outcome should go up or down, and it should be linear, a linear relationship. And linear regression, it's easy to think about it when you only have one variable. We have several, but it still kind of works the same way. It's just using each of those variables as a new dimension. And so what you get is this higher dimensional surface that is a hyperplane. And so it's not bent, there's no curvature to it anywhere. It just looks like a hyperplane in some high dimensional space that tends to, go up or down in each dimension according to those input variables. And so the first thing I'm going to do is just to see, could we do this really simply? Because we made an observation here that there are a couple really strong predictors. So what if I use just a couple variables and I forget about the rest of my variables? Let's just use 2. And so I've suggested here to use weight and displacement. And so in this to-do cell here, fill in those square brackets with weight and displacement. And so just make that into a Python list that contains weight and displacement. And so we're only going to use those 2 at first. We're going to come back to using everything, but we'll start with just those 2. And notice the name of this one is simple random var calls. So run that cell when you get it filled in. The only thing to watch for there is make sure you spell displacement. I almost misspelled it. And you can copy paste. The next cell is going to define a couple of scoring metrics. And so how do I know that my model is doing a good job? I have to measure something. And so for regression models, one thing that people tend to measure is something called R squared. And I'll come back and talk a little bit more about what R squared does, but essentially higher is better. It says how much of the variation in the outcome does your set of predictors explain, or does your model, given the set of predictors, explain? And so it goes from 0 to 1, and higher is better. And so you could think of it as a percentage. And so you could think of R squared as being, so if it's 0.8, you'd say we're explaining 80% of the variation in the outcome. And so that's good. You really want 100%. The other one that I'm using right now is something called negative mean absolute error. And I'm just calling, I'm nicknaming that MAE for mean absolute error. The absolute error just means calculate how far off you are and then don't care about the direction. And then so sklearn doesn't have MAE, but they have this negative MAE for reasons that are not interesting to talk about here, but it's measuring the same thing. They just throw a negative sign on the end of it. So it's the same measurement. It's just a negative number instead of a positive number. You really want this number to be close to 0. So essentially the magnitude being smaller is better. And so we want this mean absolute error to be near 0. And I'm putting that into a Python dictionary just so that I can use it later on when I do my evaluations. I don't have to retype these things. I can just pass it as an argument. So just run that cell and it should be good to go. Okay, so here's what this linear model is going to look like if we wrote it out in math class. So those betas represent coefficients. And so a linear model just says, I'm going to take a coefficient and I'm going to multiply it by each of my predictors. And I have 2 currently. We picked just weight and just displacement. So I'm going to take my value for weight and my value for displacement, and I'm going to assign each of them a little coefficient, which is just a number we're going to multiply them by. And then I'm going to add those together, and I'm going to add in one more thing. And this other thing is what you would normally call the bias. In math class, you would call that the intercept. And so we have the coefficients, which are the slope on each of those dimensions. And then we have the bias term, which is or sometimes they call it constant term. And that just is the intercept. If you were talking about the y-intercept of the model. All right, so now those three things, that's what I don't know. And so because this is supervised learning, I know y, my miles per gallon. I know my weight and my displacement. That's part of my data set. I don't know these betas, right? So that's what I'm actually trying to figure out. What is beta 0, beta 1, beta 2? And that's what my model fitting is going to determine. So it's going to look at the data and it's going to try to find the best numbers for those three things to cause the best possible fit. And so we don't have to, again, you don't have to get into the weeds about the math. We have a function from scikit-learn called linear regression, or it's a model called linear regression that we can fit. And so let me tell you a little about what this cell is going to do. Because there's a lot going on, because again, sklearn is really powerful. It's going to run a cross-validation experiment, which means it's going to repeat a splitting between a training set and a testing set. It's going to repeat it 5 times by default. And each time it's going to split the training set differently. So it divides it into 5 different groups. And each time it's going to take 4 of those groups and use them as the training set. And the last one is going to be the testing set. And then it alternates so that you end up using, so in those 5 different repeats, you end up using all of the values for training at least once. And you end up using all of the values for testing exactly once. And it's going to aggregate the results. And so those metrics that I have, it's going to aggregate those together. And it's going to return them so that I can print them out. And so I can print, so essentially then I can calculate the average, the mean, and the standard deviation. And I can print those out, which will tell me how good is my model at solving this problem. And so this is pretty dense. It's not a lot of code, but it's pretty dense code because it's creating the linear regression model using all default parameters. I'm not trying to customize anything. I'm not tuning any hyperparameters. And then it's setting the X value. So X means predictors. So I'm using AutoMPG at my simple random variable columns. Y, which is my outcome, I'm setting to AutoMPG at the target column. And then for scoring, I'm saying use these scoring metrics that I just defined above, which is R squared and mean absolute error. And so then I print them out. And so I'm just printing them out with a little bit of formatting to say I don't want to see too many decimal places. So that just makes it look nicer. And that's just using Python's F strings, so Python's formatting strings to do that. And notice that I'm sticking a minus sign in front of this MAE because they're giving back negative MAE. And so I'm just flipping it so it looks nicer to look at. If we run it, it's actually really fast. And so that did an entire experiment 5 times, and we aggregated the results. And it happened, in less than a second. So it was really fast. And here's what we see. We see the mean R squared across those 5 trials was 0.326. And it had a standard deviation of 0.523. We see that the mean MAE, which is mean absolute error, and the nice thing about mean absolute error, it actually comes back to you in the same units as the thing you're trying to measure. And so here, we're trying to predict miles per gallon. And so MAE is in miles per gallon. It's absolute error. So it's the number of miles per gallon that we were wrong on average. And so again, we'd like it to be 0, but it isn't. And so here it's 3.8 with a standard deviation of 1.4. And again, those are miles per gallon. Okay. Well, this is not great. So I don't know how many different models you've looked at, but having an R squared of 0.32 is kind of sad. That's not doing a very good job. Again, we could look at this as saying this model explains 32, and let's round it up to 33. It explains 33% of the variation in miles per gallon, which is not much. So it's a pretty weak model, really. And again, looking at these statistics, it worries me a bit that the standard deviation was 0.52 on an R squared of 0.32, so the standard deviation is bigger than the R squared. That's telling me that there's a huge variation from one of these trials to the next. And so what that's telling me is the model isn't stable. Exactly which samples it trains on is making a big difference in how it performs when I run it against a test set. That's bad. It means that it's very sensitive to getting just the right samples, which also means this model is not going to generalize well. And so if I put this thing into practice, it's not going to be very trustworthy. So everything here is kind of bad news. And we could talk about why that is, but for now, let's just suffice it to say we could do better, maybe, right? That's not great. For those of you that remember when I said it's not really good when you see lots of correlation between your predictors, that's one of the things that might be causing problems here. There's some other things, but that's one of them. I see there's an error. So someone in the chat has an error. Oh goodness, that's so small. Let me see if I can zoom in so I can see that. Okay, that key error, it says displacement is not an index. There is a spelling error. So when you had so scroll back up to the place where we created, so the cell where we created simple random var calls, scroll back up there and check the spelling on the word displacement. I think you misspelled. And that's exactly the same thing I did. I was talking and typing and I misspelled the first time. And you can copy and paste it from that comment on the line above if you wanted to. And once that is spelled correctly and you rerun that cell, then you should be able to come back down to the cell where we do the cross-validation, and it should work. See if that works. Awesome. Good news. Some ways you can handle multicollinearity. One of the things you might look at is PCA. And so, again, it's not really part of this talk, but we could, if we have time at the end, we can come back to that. And so I think that's a good question. That is something that I cover in the unsupervised learning, the clustering. I think I do in the clustering talk. Actually, don't hold me to that. Maybe it got cut. But yeah, PCA, I think there is at least one workshop that will talk about that. But I think hopefully we'll have time at the end to talk about that some more. Because that is a common problem and you're going to run into that in your data sets. The good news is scikit-learn makes it pretty easy to do. And so it's not so hard to do. Okay, so I think we all have these results, even though they're not great results. Well, so there's a regression model, just not a great one. So let's see what we can do. First of all, let's scale this up a little bit. So instead of just using 2 predictors, let's use all of our predictors, right? So those 2 predictors, essentially I did that so we would have something to improve on. And just because if we could do a really good job with only 2 predictors, then a simpler model is usually going to scale better. Usually it will generalize better. But we can see from our numbers here that this model would not generalize very well. So let's try putting everything in there. So I'm going to do exactly the same thing. And so this code looks just like the previous cell, except now I'm using random var calls, so all of my random variables, instead of just the 2. Other than that, everything's the same. So I'm performing exactly the same experiment again, just using all of my, I think it was 5 random variables. And so when you run it, again, it takes less than a second. It goes really fast. And we see, okay, this is better. So the R squared now was 0.571 and the standard deviation was 0.231. So that's a decent, that's a decent amount of improvement. So now we're explaining more than half of the variation. So that's good. It's not great, but it's good. our standard deviation went down pretty significantly. So notice that the standard deviation is now smaller and much smaller than the R squared itself, which means exactly which samples I train with is having less of an effect on the final product, which means my model is becoming more stable. So it's more likely to generalize if I put this into practice. Now, that's still a kind of high standard deviation. I'd like to see it a bit lower, especially with an R squared as small as 0.57, but it's a big improvement from the previous one. Now the MAE, so now we have gone from 3.8 miles per gallon mistake on average to 3.1 miles per gallon on average. And our standard deviation there improved too. So it improved quite a bit. And so what this is saying is this particular model, if we stopped here, would be able to predict most cars within about 3 miles per gallon. Okay, which is, I mean, not too bad. Right? That's not too bad. So let's see if we can do even a little better. So we're looking at different kinds of models. So as you're looking at which model should I use, my recommendation is always pick the simplest model that will do a good job for you. And so if I had really great performance from this linear model, I would say this is what I want, because a simple model that solves your problem will tend to be easier to explain and easier to reproduce. And so your explainability and your reproducibility has gone up. A simpler model that solves the problem well also tends to generalize well. And so when you put it into practice in the field, it usually won't surprise you. It will keep working as well as it did when you tested it in the lab. More complicated models, that's not always the case. Sometimes it's harder to make them generalize. And so there's more that can go wrong. But we're not really happy with our R squared or our MAE here, so let's see if we can do better. So I'm going to try a polynomial model. Now, good news and bad news. The bad news first. Scikit-learn does not have a polynomial regression model just built in. The good news is you get a polynomial regression model just by using a linear regression model on transformed features, and sklearn can do that for you. And so what you see here is I'm creating this thing called a polynomial features object, and I'm saying give me a polynomial of degree 2, which is quadratic, and I'm saying don't include the bias because my linear model later is going to put the bias term in there for me, and so I don't need to do it here. And so I'm calling that thing poly. And this time when I create my model, I'm still creating a linear regression model, but what I'm feeding it for its input, for its predictors, is this polynomial fit. And so I'm doing a fit transform of my predictors. And so this is doing a data transformation. Now, I did it kind of all in the same step, inside cross-validate. You could have done this as a pre-processing step, and so you could have transformed your data set so that it had these polynomial columns in there all the time. That's kind of up to you, how you wanted to do that. And so I'm doing it just as needed. So I'm just dumping the transformed data directly into the fitting function during cross-validate. Everything else kind of stays the same. So my Y is still my target column. My scoring metrics are the same. And I'm still measuring and printing out R squared and mean absolute error. So if we run it, again, this should be pretty fast. We see a better number. And okay, if you've done any kind of mathematical modeling, you should be expecting this, right? As a model gets more complex, it has more power to fit your data set. And so we would expect as we make the model more complex, our performance should kind of go up. Now, the trouble is sometimes your ability to generalize goes down. And so we need to keep a close eye on our standard deviations as well. So here our R-squared value went up. So now we're into the 60s. So 67, that's starting to be reasonable. That's starting to be actually pretty good. Our standard deviation actually still went down. So we were at 0.23, we went down to 0.22. So almost the same, but it didn't go up. And that's important because it means that my model is still likely to generalize pretty well. And so we're not overfitting. My MAE also went down, and its standard deviation, let's see, it went up just a tiny bit, but that's essentially the same. And so I'm still pretty confident there that that model is okay, right? It's doing within 2.6 miles per gallon each time.
Sorry for the interruption, but this is about the halfway point. So if you want to take a 5 to 15-minute break, please stay in your breakout room whenever your instructor says there's a good breaking point. Thank you.
Thank you. Okay, so as soon as we finish this talking about this cell, we will take a break. Yeah, so this model's doing a pretty good job. So it's an improvement. We can maybe do even better, and so we'll talk about that after the break. But this is, polynomial regression, so we've kind of ratcheted up the complexity of the model. We've improved our performance reasonably well, and so far we're actually seeing that we're still improving our ability to generalize. So the standard deviation of the cross-validation is pretty good. There's a question there in the chat. Is it okay if we do standardization initially just after loading the data? The answer to that is maybe. So that's a more complicated question. Lots of people do that. They do standardization on the entire data set. You can, so technically speaking, you probably should not. And the reason you should not is if you're doing standardization on your entire data set, and then you're splitting it into a training and testing split, or you're doing cross-validation, splitting it into smaller pieces, that standardization is a way of changing your variables so that they fit a particular set of statistical assumptions. And what usually happens is it takes your variables and standardizes them so that they have a 0 mean and a unit or a 1 standard deviation, which means you're looking at all of your data at once. That means you're leaking a tiny bit of information across your train test split boundary. And so ideally, you do your standardization on your training set within your framework of doing cross-validation, and then you save the parameters, you save those statistics, and you do them the same transformation without refitting, the same transformation on your test set. And so that will give you the best possible unbiased measurement. And so that's a really good question. That's really down in the weeds. But yeah, a lot of people do it initially just after loading the data, but technically speaking, that's not the best idea. And we can talk about that more at the end if you want. We'll take a break here. So let's take about 5 to 10 minutes and we'll start up again. All right, welcome back. We've been looking at regression models, and we just finished looking at the polynomial regression. And so we saw there that you have to do 2 steps. So there's not just one model for it in scikit-learn. By the way, some of you are also looking at R. I think in R there is a model that can do it in just 1 step. But here we have to do 2. So we have to create this conversion tool that's going to transform our data and add the polynomial, the x squared columns to the data. And then we just use linear regression. And so we did that. We saw that we had a pretty good improvement in the performance. And so that's pretty nice. And so now we're, 67% R squared, bordering on 68%. That's pretty good. And so this model is starting to look promising. Let's see if we can do a little better though, because everyone says, well, linear models, those are boring. Polynomial models, those are boring. What else is there? So let me show you a more powerful model, and this one's pretty powerful. And then we'll look at a few more things. So we'll look at, how do we tell if we're doing a good job or not, other than just looking. So far we're looking at numbers, and it's easy to look at a number and say, okay, if the number goes up, that's good. Or if this MAE number goes down, that's good. But it doesn't tell the whole story. And so we'll look at other ways of evaluating these models. So I do want to look at a random forest regressor, because this is something that makes none of the assumptions that these linear models have been making. So those things like, are there relationships between the predictors? Random forest models really don't care about that sort of thing. They're pretty robust to a lot of the problems that can cause trouble with other kinds of models. Now, they have some of their own problems, but in general, they're pretty robust models. And so there's a random forest classifier that most people are familiar with, but there is also a regression version of a random forest. And the way a random forest works is it uses trees, so decision trees, and it uses a whole bunch of them. And so that's why they call it a forest. It's a little play on that, the fact it's built up of decision trees. And so each of these decision trees looks at one of your predictors or maybe more than one of your predictor, and it tries to make a decision about what it should do based on the value it sees in that predictor. And so in a random forest, you have hundreds of these trees or maybe thousands of these trees. And at the end, they all, well, in a classifier, they would vote for which is the right label to apply. In a regressor, the equivalent to voting is averaging. Essentially, they average up their predictions. And then they come to a kind of a group or a community consensus on what's the right number. And that's what they return to you. And it can work really, really well. And so here, we're going to set one up. Again, scikit-learn, great about this because it can, it just has a model called Random Forest Regressor. Pretty much works well without doing a lot of meta analysis or meta tuning. There are some meta variables that you can tune, so it is tunable. Most of the time, you don't really need to. It works pretty well out of the box. In our case here, the only thing I'm doing is I'm putting in this thing where it says random state equals 1. I'm doing that to make it reproducible. Because if I didn't do that, the word random forest, there's something random happening in there. Every time I ran this code, it would give me different answers. And that's not really what I want. I want it to be somewhat reproducible, just so that the notebook looks the same and I don't get surprised from one run to the next. And so I'm putting that random state equals 1 so that I'm reducing the places where something can change from one run to the next. So I'm going to do that. Everything else I'm leaving at default. I'm still using this cross-validate function from sklearn. I'm just using all of my random variables for predictors, and I'm using my target column to select the target, the output variable. And I'm collecting exactly the same scoring metrics. So I'm collecting R² and MAE, the mean absolute error. And so pretty much the same. The only thing that really changed is what model am I using? So what's its name? And I'm setting this random state just to make it reproducible. So if we run that, it's going to run. It's going to be pretty fast. Again, so this thing's doing its work. It's still, this is a much more powerful model, but it's still pretty fast. And we can see, well, this is even better. So now my R² is up almost 75. So I'm at about 75% R². That's really kind of starting to get into the, oh, that's pretty good range. I mean, I would really be happy if we had a 90%, a 0.9 R², but 74.8 or 75 is not bad. Notice that the standard deviation still went down. And so we were at 0.22, now we're at 0.198. That's good. That means my model is getting better, but I have not run into what I would think of as an overfitting problem. So it's not getting, it's not having a tendency to perform erratically depending on which data I'm training it on. And so that's good. The MAE improved a little bit. So we went from 2.6 miles per gallon error down to 2.2. So that's the right direction. It's not much of a change though. So it's, we're kind of finding that the improvement is less dramatic on the MAE. And that's, in a way, that's to be expected. The miles per gallon is one of those things that there are some interesting outlier values. And so it's hard to be perfect on that. Right. And so this is even better. So now I have a model that looks like it's doing pretty good. And so again, I would say I would be pretty confident in putting this model into practice. Again, if I'm happy with that performance. Ikram, do you have a question?
Yeah, I had a quick question about the random states. Generally speaking, would you say it's better to keep it at one, or is it more, does it give you like, I guess, better understanding of what the model's doing if you remove it? Or like generally like out in the world, do people usually like keep it at one, or do they usually try to like let it be random so they can see how it's doing it at different ways?
Um, it depends on what you're trying to do. So if you want the thing to behave differently on different runs, then you would just leave it out and it's going to do whatever it does on that particular run. That can be good if you just want to train the model and then go on about your business. If you want it to be reproducible, then you really need to set a random state. Now, one is so that random state could be set to any number. And so one just happens to be the first number that I picked. It could be anything. Sometimes I pick, like favorite numbers or like the year or 42 or something. All that's doing is it's just picking one possibility out of, every possible possibility of initializing that random number generator, just so that every time I do it, it's going to do the same thing. It doesn't really matter which one you pick. So if you are trying to make it reproducible, you can pick any number you want. Now here's where it gets interesting. If you change that number, so if I change it from 1 to 2, the performance will change a little bit. And so I'll get a different initial state. If I run it again, I'll get different numbers. And so here, it got a little bit better. So there's 0.75. Right, so it changed a little bit. If I go to 3 and if I run it again, so it's about the same. So that was about the same as 2. If I go to, some other number, it's going to change again. It'll be just slightly different each time. But if I rerun it again, it's going to give me the same result as long as that number stays the same. It's going to keep giving me that same result. And that's what we want for reproducibility. And that's, again, usually in research, in science, reproducibility is a big deal. And so we usually do want that. Now, so I pick one and I run it. There is a certain amount of, you would call it luck in this. If you feel like your results were unusually bad, you might pick a different random state just to see if it makes a significant difference. So there is some chance, it's a vanishingly small chance, but everybody always kind of feels superstitious about it. If they don't like the number, they say, well, did I get unlucky? And they'll pick a different random state. Again, fine, that does it. So if your performance changes dramatically from one random state to another, that's a hint that you probably have a problem. Right? It really shouldn't change much. And so it shouldn't matter much which number you pick. And again, that variation should be well within your standard deviation. And so you shouldn't see that variation making a big difference.
Okay. And so it's basically like each number you choose is like the thinking pathway it chose to like execute the function.
Yeah, so in random forest, there are some things that it's doing. Basically, it's rolling a dice. It's doing something random to choose things from one step of the process to the next. And that randomization gives you diversity inside when it's building the model. So it's important to the way the model works. But again, for reproducibility, we want to make sure that it's doing a thing that is unpredictable, or it looks random to the model, so the model still works, but is reproducible. And so all that setting that random state does is it makes it so that the random number generator starts at the same point. And so, computers don't really usually have true random number generation. They generate a series of numbers that fits a certain distribution. And so a random number generator is really just a uniform number generator. And so when I set this thing's random state to 1, I get a series of numbers that look random, but if I run the program again, I get exactly the same series of numbers that looks random. Does that make sense?
Yeah, that makes sense. Thank
So
you.
things that need that randomness can still perform, but now every time I run the program, it will perform the same way. And so it's reproducible. Now, if you were making a game, you don't want to do that because now the players, everything would happen exactly the same when you replay the game, and it wouldn't be any fun. And so you would leave it out. Certainly, if you were making something like a game.
Okay, thank you.
There's a good question in the chat there. Is there another model we could use to get an even better R squared? Yes, and there's an excellent suggestion there. XGBoost, or maybe a neural network. Yes, that would probably do. So again, adding complexity, using a model that has more complexity, more capacity, will tend to give you better performance up to a point. The risk is that you also may start to overfit. And so again, here we're kind of keeping an eye on, we're keeping an eye on our performance, but we're also looking at the standard deviation from one of those cross-validation runs to the next. And we're making sure that number doesn't start going up. And so you just have to be careful. But yeah, XGBoost would be an excellent choice. On this data set, I probably wouldn't use a neural network just because the data set is not really large enough. And I don't think the neural network would give you any advantage over XGBoost. But XGBoost or LightGBM would be really good choices if you absolutely want to do the best performance you can get. Okay, so I want to shift gears a little bit here. We could keep talking about different models and kind of writing the code to work with different models. But the truth is it's going to keep looking like the same bit of code over and over again because most of these models are built into sklearn. The process for training it, validating it, and then printing out the performance looks the same. And so the numbers are going to change a little from one run to the next, but the process is the same. And so I think once you've seen how to do this with these models, now you could decide, well, if I want to do this with XGBoost or LightGBM or some other model, you can just plug it into this framework and it's going to work. So what I do want to look at is now how do we look at the performance of this model that we've trained and say, is it doing a good job? Am I happy or am I not happy? So I want to come back to visualizing because I like to look at things. So that's something, so far we've been looking at numbers. So what I'm going to do in this next cell is I'm splitting the data set into a train test split. So here I'm not doing that 5-fold cross-validation anymore. I'm doing something that's simpler just because it makes it easier for me to show you what I'm going to show you. In a real experiment, if you can afford the time, the problem with a k-fold cross-validation is it takes time. Now, we saw that it's pretty fast. So all these things we've been doing have been taking less than a second. And so there's really no excuse not to do a cross-validation. But in those cases where you don't need full cross-validation, you can just split into a training set and a testing set. And just so that we see it, there's a train test split function in sklearn that will do that for you. And so we put in our data. So here's our random variable columns. Here's our target column. We say I want my test size to be 20% of the data. So this is going to make an 80-20 split. And again, I'm setting my random state. I just set it to 42 just because that's a fun number. And that it's going to give me the same split every time. Otherwise, it would give me a slightly different split each time. And what it gives me back is a group of data frames. And so this xtrain is my predictors for training. And then I have my predictors for testing. I have my target column for training. And I have my target column for testing. And so it gives me back those 4 things. So with that, I'm just going to train a plain old linear regression model. So I'm going all the way back to that linear regression model by default with no parameters. And so here's another to do. So see if you remember how to type that in. So it was just literally the words linear regression with camel case, so capital L, capital R, and then a set of parentheses with nothing in it because there's no parameters. We're not trying to tune anything. And then once we instantiate the model, I'm going to immediately fit it. And so I'm going to fit it so that X is xtrain and Y is ytrain. So the code that you're filling in, you're replacing the word none with that. So linear regression, parentheses, dot fit. And then you don't even have to put the X equals Y equals. You could just say xtrain, ytrain. Everything else is already done in this cell. So what it's going to do next is it's going to make predictions based on the test set. So we put the predictors in for the test set. It's going to make its predictions. And so I'm calling that linear preds. And then I'm going to calculate the residuals. And so residuals just means how much of a mistake did we make on each of them. And so it's going to calculate those residuals. I'm storing that in linear residuals. So I'm taking y test minus my predictions. And so those could be positive numbers or negative numbers, depending on whether I over or under predicted. And then I'm just going to plot them. And so I'm telling Matplotlib to create a new figure for me and create a scatter plot, which means plotting one variable against the other, and it's going to be dots. And so I'm plotting my linear predictions against my linear residuals. So predictions will be the x-axis, residuals will be the y-axis. And then I'm also adding a line in there at y equals 0. So 0 means no error. So that's where we want to be. So I'm going to draw a red line so that we can see where we want to be. And I'm just putting some words on it. So labeling it the x-axis, the y-axis, and putting a title. And so if you have typed this in, so this is the part you're typing in. If you type that in and click on run, it should work pretty quickly. And this should be what you see. Okay. Let me know if that doesn't work. So everybody, if you try that out, hopefully we see that it works. Now, here's how we interpret this. Every dot means a mistake. And the dots are ordered according to, increasing miles per gallon on the x-axis and increasing residuals on the y-axis. And we want them, we really would like to see all those dots just crowded along that red line, but that's not what we see. There's some mistakes. What we would like to see, given that there's going to be some mistakes, no data set's perfect. What we would like to see is that the residuals, those dots, are just scattered randomly. They don't have any pattern. And so I had a statistics teacher once who described it as you want to see the sky at night. You just want to see a scattering of stars. Is that what we see? Does anyone else see a curve? I think I see a curve. Yeah, so half positive and half negative, that would actually be good if there was no shape to it. But it seems like early on, for small miles per gallon, it's over predicting, or is that under predicting? Anyway, my residuals are on one side of the line, and then they move to the other side of the line. And so it's predicting down here, and then it's predicting up here again. So there's this curve, there's a shape. That tends to be bad news. And so, okay, this is a linear model. What that almost immediately tells me when I'm looking at a residual plot like this, that tells me that maybe this problem was not linear in nature. And so there's some nonlinearity in the problem. And so maybe a linear model is not the best choice for solving this problem. And so again, this is something I would probably do early on when I created that linear model and we didn't really like the R-squared. Plot those residuals, look at it, and then when I see this kind of smile, this curve, that also tells me maybe a linear model isn't going to work at all. And so stop chasing that one, move up, ratchet up to a more complex model. And so maybe a quadratic model, because we do see kind of that curve.
Please, can you show the code for the linear regression? Yes. Thank you.
Yes, right here. There was a question, so while you're looking at that, there was a question in the chat. Is allocating 20% of the data set for testing a widely accepted norm, or does increasing the test set proportion have a notable impact on model performance? That is a good question. So the trouble is there's not really an industry norm, but I will say that an 80-20 split is a common choice. There are some trade-offs, and so you choose the size of your test set according to some different pressures. The first pressure is training set size. So the opposite of that is we have 80% of that data for training our model. Depending on the size of your data set and depending on your model, you might be happy with that, or you might wish you had more training data. Now, a lot of the work I do is in neural networks, deep learning. We always wish we had more data. We never feel like we have enough. And so if we have a really, really huge data set, I might reduce the test set size down a little bit just so that I get more training data. And so maybe I could go to 85-15, or maybe I could go to 90-10 and get more data into my training set. On the other hand, as that test set gets smaller, you lose a little bit of statistical power. And so you want your test set to be big enough that if there's going to be a problem, if your model is going to be inconsistent about its predictions, you have enough data in your test set to reveal that. And so your test set should be statistically representative of the population. So you can't push it too small. And so so from that standpoint, I want to make it bigger. I want to make maybe a 70-30 or a 50-50. All of these things are possible. And so it's kind of competing concerns there. Only you know, because only you know what your data set looks like and what your model is going to be and what your needs are. And so you have to kind of make that decision on your own. 80-20 is pretty common though. So that's a good, if you don't know what else to do, 80-20 is a good starting point. And by the way, if you're doing a k-fold cross-validation, 5-fold cross-validation is the most popular because it happens to be 80-20. So every single fold, you're getting 80% in the training set and 20% in the testing set, and then it reshuffles. But you will see people do other folds as well. So 3-fold is sometimes used, which ends up giving you a bigger test set. 10-fold, I've seen 10-fold cross-validation, which gets you your 90% 90-10 split. And so people push it both ways. And so you will see that even in k-fold cross-validation. Okay, is everybody able to get the fit to work so we can see the plot?
Yes. Thank
Awesome.
you.
You're welcome. Okay, so we think this is not a great fit, right? We look at that, we see a shape, and we say, maybe we can do better. And so in this next cell, I'm going to do the same thing. I'm not going to do this for every single model. There's no need. Let's just skip to the one that we thought was best. And so I'm going to try it again with the random forest. So here we're going to train the random forest model. Again, I'm retraining it using my train test split just because I want a fair comparison. So I'm going to use that same training testing split. I'm going to make predictions exactly the same way as before, calculate the residuals the same as before. So this is identical. And I'm choosing my random state to be 1, just like I did before. So everything's fair. And we'll see what we see. So there's the residual plot when you run that cell. And so there's nothing for you to type there, so it should just run. It should just work. And we can look at that. Now, the good news is it's not smiling at me anymore. I don't see a curve. And so random forest models are nonlinear in nature. And so it was able to handle the nonlinear properties of the data set. So that's good. I see some of the data above the line and some of the data below the line. That's what I would expect. It would actually be bad news if all the data was above or all the data was below. So it's missing, kind of alternately above and below. That's good. So overall, this is an improvement. It's not perfect though, because I still see something that's a little weird. On that left-hand side there, when you're looking down at the lower mile per gallon, so around 15, between 15 and 20, it's doing a pretty good job. But there's not much error at all there. Those dots are very close to the red line. When we get between about 22 to about 32 miles per gallon, well, now we've got a big spread. So suddenly this thing has ballooned out and the distance along that y-axis got a lot bigger. It also seems like there are more dots below the line than above the line. And so there is still a little bit of a pattern here. It's not as pronounced, but it's still there. And then from 30 miles per gallon up, that trend of where is it missing? Is it missing above or below the line? Is turning around and kind of reversing. And so it's not perfect. There's still some problems, but it is better. So this does verify that we improved, but we still don't have a perfect model. All right, so another way to do this. So another way to visualize the errors. On this next code cell, what I'm going to do is I'm going to plot scatter plots again. I'm going to plot the actual values versus the predicted values. And so I'm going to literally put what did I predict versus what was the truth. And then I'm going to plot, well, normally what you do here is you would plot a line that runs from the lower left to the upper right. So you would plot essentially a line that should fit perfectly. I don't think I did that in my code here. I didn't add that line. Let's see what this looks like. Oh yeah, I did. Where did I put that in there? Oh, there it is. Yeah, okay. So I put the line in there. That second line each time. And so you'll see here, so this is on the left is the linear regression model, on the right is the random forest. And similarly, we see a difference in the plots. And so the linear regression, again, you see it has a curve to it. And so the way it's missing the truth line changes. And with the random forest, you can see it's fitting closer along that line. But again, sometimes it's missing one way and sometimes it's missing the other way. And so you can see where it's over predicting a little bit or under predicting later on. And there's a related question in chat. Is there a reason that it's bad with the high miles per gallons, or was it random? Well, there is kind of a reason. And if we go all the way back, and so I'll let you guys look at this plot for a minute. If we go all the way back to that scatter plot in the beginning, the reason is that the miles per gallon become more, they have a higher variance in the higher miles per gallon. And so if we scoot all the way back up here to the top, let's look at first of all, the histogram of miles per gallon. Notice that it's not normal. It's not centrally distributed. It's kind of tail heavy. Most of the weight is on the lower miles per gallon. So it's kind of weird. There's very few in that first bar, and then it gets really tall. And so most of the miles per gallon are between 12 or 15 there, up to, mid 20s. And then it drops off pretty sharply after that. And so there's just more data with the smaller miles per gallon than there are with the higher miles per gallon. And then again, if you look at the way things are distributed, so looking at some of these scatters of things versus miles per gallon, you'll notice that they tend to have this curve that exacerbates, or the curve changes when you get into those higher numbers. And so it's this combination of most of my data is at the lower numbers, and so models like the random forest can fit that better because they have more data to work with. And the curve, the thing that's nonlinear, is worse when you get into the higher miles per gallon. And so you have two different factors that are affecting you essentially both in a negative way here. And so that's working together to make that part of the problem harder. Good question. One thing to consider, so again, while we're looking at this plot, if you see this, so if you're running into this trouble, and I suspect with this one, even a more capable model, so maybe XGBoost is powerful enough that it can correct that without you having to do any extra work. But it's not uncommon for something like this to happen and it's too severe for you to correct. And so one of the things is when you look at that histogram, the way it was skewed. More of the value was at one end of the histogram than the other. This mile per gallon data set, it was somewhat skewed, but it wasn't terrible. That gets a lot worse. And so sometimes in things like salaries or housing prices, you'll get a case where almost all of your probability mass is at one end, and then it drops off almost like a hockey stick. It drops off really sharply when you go the other way. If you see that, that's what's called a power law distribution. And those things are monstrously hard to correct for in a model, especially when it's your target variable. And so if you see a really bad skewed distribution like that in your target variable, you might consider transforming your target, for instance, using a log transform to try to remove that really bad curve. So make it into something that looks more normal before you start trying to fit a model to it. And then what you're actually trying to predict is your transformed version of your target variable. So here, if we did it, we might log transform miles per gallon, although I think that's too aggressive. This is not a power law, but it's a, I don't know, maybe something like a square root would make more sense. But we do some transformation of the target variable. Then we try to predict that transformed variable, which you could probably do a better job of. You just have to remember that when you actually make predictions, you have to undo the transformation. And so, if you did a log transform, every time your model predicts, you would have to take, if you did natural log, you would have to raise e to the power of your prediction to get back your actual miles per gallon. And so it makes it a little more complicated because you have to untransform when you make predictions. But it could also mean the difference between a model that just doesn't work and a model that works pretty well. Right. So those are the visual metrics, so ways of looking at something and saying, does the model look good or not? Some more non-visual metrics, and we've already been seeing some of these. And so I've just collected some together here that we can look at. So in regression models, it's really common to use MSE, mean squared error, as a metric. Mean squared error, and by the way, there's a link. If you want to know the formulas for all these models, you can go to this sklearn page and it shows the formulas. How do you calculate them by hand? But mean squared error is just looking at the mistake between each prediction and its truth, the ground truth, and then it squares those differences and adds them up, and then takes the average of that. Smaller is better, and so mean squared error goes from 0 to essentially infinity. It's unbounded. Big numbers are bad, small numbers are good. And so it's really easy to calculate, and it's easy to interpret in the sense that smaller is better. The bad news about mean squared error is it's hard to interpret in the sense that a squared mistake no longer has any meaningful units. So what is a squared mile per gallon? It's not something we can reason about. And so that brings us to the next one. So RMSE is root mean squared error, which is almost the same thing except that you take the square root of it. And so there isn't a built-in RMSE function in sklearn. You just calculate your MSE and then you square root the whole thing. And so the advantage of RMSE is it brings your units back. And so because the error was squared, when we square root it, it untransforms, and now we're back to having miles per gallon error. Now, the other way to get that is this mean absolute error. And so mean absolute error is the thing we've already been looking at. So it's just taking the absolute value of the mistake and then taking the mean of that, so taking the average. And so again, the advantage is it's in the same units as the original thing. And so if you're measuring miles per gallon, MAE is coming back to you in miles per gallon. And so you can reason about it. So the question there in the chat, RMSE is like the average residual. Actually, that's MAE. So MAE is closer to the average residual. Again, only we don't care about the sign. RMSE is not quite that because you're squaring the mistake every time. And so squaring and then unsquaring it, it's kind of the same, but it's not exactly. Again, that absolute error would be closer to that because residuals are just a straight calculation with no squaring. But both those numbers are going to be very similar. And well, how do you know which is good? Smaller. Right? You want to make smaller mistakes, and so better is smaller. Whether it's MSE, RMSE, MAE, all of these things that are measuring error, so similar to residuals, smaller is better. You want it to be 0. The further it gets from 0, the worse. Now this MSD, so MSD, I had to remember in my head what that means. It's the mean sign displacement. That literally is the average residual. And so here we're just taking our predictions, subtracting our test, and taking the mean of it. Now the thing about MSD, so again, good things and bad things. It's in the right units. It's in miles per gallon. It has a sign, and so if my model tends to be over-predicting most of the time, it's going to be a positive number. If my model tends to be under-predicting most of the time, it's going to be a negative number. Right? So the sign will tell you direction. The bad news is it also, so the positives and negatives kind of cancel each other out. And so some people don't like MSD as a measure. Usually you would use it in conjunction with something like MSE to tell the whole story. It is usually interesting to know in a regression model, if my model is making mistakes, which direction? Does it tend to be over-predicting or under-predicting? And that's usually interesting. And so MSD can tell you that. If your model is very biased one way or the other, the MSD error will, so that the mean of the residuals will tell you that. And then finally, R squared, we already talked about R squared. That's just the coefficient of determination, or it's the amount of variance in your target variable that your model is able to predict. And so we end up calculating these things for each of our models. Did it for linear regression and for random forest. And then I'm creating a data frame from that. And so we can see that as a data frame here. So you can compare. And so linear regression is pretty much worse on every metric. Right? So you can see there, again, with almost all the metric, with every metric except for R squared, smaller is better, or with MSD, closer to 0 is better. And you can see here that the only thing, so actually random forest, MSD was worse on random forest in a way. So random forest is tending to over-predict more than linear regression. So that's kind of interesting. Everything else, random forest did better. The next thing you might want to know is, okay, I have this model. It's performing okay, but why? Which of my features, which of my variables was actually the good one? A misspelled feature, look at that. So we want to know the importance of each of the features. Some models make it really easy to figure that out, and some models make it a little harder to figure that out, to the point where if you get into deep learning, feature importance can be an extremely challenging thing to figure out. But there are some tools out there to do that. I just want to look at a couple. So again, let's look at the extremes of what we did. I'll look at linear regression, and then we'll talk about the random forest. And so with linear regression, the coefficients themselves are a measure of feature importance. The bigger the coefficient, the more of that variable the model is using to make its prediction. That's the way you can look at it. And so if you want to figure out feature importances for a linear regression model, you can literally just look at those coefficients, take their absolute value, so how big is the coefficient, and then sum it up. Now, the thing that I'm going to do here is I'm also going to, when I sum it up, I'm also going to divide by the total, the sum. So I'm going to make this thing between the range of 0 and 1 for each of the features. The reason I'm doing that is just so it makes it easy to compare, because those coefficients are not required to add up to 1. And so for just human friendliness, it's nice for the most important thing to be the thing that's closest to 1 and the least important thing to be closest to 0. And I'm going to create a data frame for it. I'm going to sort them by their importances. And then I'm also going to plot it in a plot. Okay. And so the plot ends up looking like this. So it's just a bar graph. And so we can see here that model year by far was the most important feature in that linear regression model, followed by cylinders, followed by acceleration. And then honestly, everything after that is almost negligible. Weight mattered somewhat. But again, remember how much correlation there was between some of these variables? By the time you have cylinders and acceleration, you pretty much already know weight, horsepower, and displacement. It's almost redundant. And so you can see the model's not making much use of those others. So good to know. Model year was very important. Now, let's think about it. Why would model year be important for predicting miles per gallon? Maybe your government is making laws that say cars have to be more fuel efficient over time. And so suddenly you get this strong prediction, this strong relationship between when was a car produced versus how fuel efficient was the car. And we see that happening here. Does that make sense? So this comes down to interpretability. How do you interpret your model? Now, if you want to know, so the thing that didn't tell me, it tells me which one's more important. It did not tell me the direction. And so now that I know model year is more important, I can look at the coefficient. So again, in sklearn, you can get the coefficients to the linear model. If that coefficient has a positive sign, it means that as model year gets bigger, the miles per gallon gets higher. If that coefficient has a negative sign, it means that as model year gets bigger, the miles per gallon goes down. And so it tells me if I have a positive or a negative relationship. And so you can see that from the coefficient itself. And so here we get the importance from the sign of the coefficient, you get the direction. So which way is it influencing? Right. And so let's do the same thing for a random forest. So random forests work completely differently than linear regression models. And so we don't just have a set of coefficients that we can look at. The good news is sklearn already knows about this and they know that we care. So they have built in this thing they call feature importances, spelled strangely. Notice there's an underscore at the end of that word. That's not an accident. sklearn does this with some of its attributes. It's just a weird design choice that they made in that library. And so this thing it's literally called from our model, it's called feature underscore importances underscore. Now notice that you have to do this after you have fit the model. And so when you fit the model, it learns the model, but it also is building this set of feature importances. And so after we fit the model, we can ask it for this number, or numbers for each feature. And then I'm going to do the same thing. I'm going to create a data frame from it. I'm going to sort it according to importance, so I get the most important thing at the top, and I'm going to plot. And when we run that, we see, interesting. Random forest found a different feature more interesting. So in the random forest model, it made more use of displacement. Now notice that model year is still somewhat important. So a couple of interesting things. Random forest is making use of more of the variables, and the most important variable is different. So why could that be? One of the things is that the linear model is assuming linearity, and so it's going to work best when its input variables are linear in nature. Displacement was not. When we plotted those things, we saw that a lot of these variables have a curve to them. They're not really a linear relationship with the outcome. And so it's not a surprise that the linear model locked onto something that has a more linear relationship with the outcome. Again, if we scroll all the way back up, if we look at model year and its relationship to miles per gallon, which is this last plot, it's fuzzy, but it's almost linear. While the other ones have, like displacement is the second one, and it's got a whole lot of curve to it. And so the linear model didn't like that. And so the linear model used model year, which was much more linear. It found that more important than the other things. The random forest didn't care about linearity, and so it found displacement more useful, and so it used that. Does that make sense? Okay. Now this,
Yeah.
so what this doesn't tell us, again, that importance number doesn't tell us which direction. And so if we wanted to know direction, we would have to interrogate this a bit further. That's a little more challenging with a random forest model. You would have to look at, okay, you would have to look at displacement for different samples and how the random forest model tends to predict them when it's given that value. And so there's a couple ways you can do it. You can do it by tinkering around with the samples and changing the displacement number up and down and seeing what happens. You could do it. I would do it by plotting, plotting displacement versus mile per gallon. If you can see a trend there, that's going to be the way the feature importance matters. There might even be something that you can get to from within sklearn that will tell you that sign. I'm not sure on that one. I would have to look into it. But you can go to the website and look at the documentation. There's a lot more in there that it can do. All right, so that is evaluating a model and sort of explaining why the model is doing what it's doing. What is it looking at for these different models? Which brings us down to this one last thing I wanted to come back to, which is what do we do when we have features that are not numeric? So what do we do when we have categorical features? And so categorical features just mean things that are strings or things that act like strings. And what generally happens with these things is we have to convert them. And there's a couple ways to do it. So here I'm using this origin. And so those levels 1, 2, and 3 are American, European, and Japanese. And so I built this little map from a number to a word, just so it makes it easier to understand. And then I'm going to plot. So we have origin 1 means American, and so on. And so if I visualize my mile per gallon according to origin, it looks like this. And so here's some box plots. So interesting. It seems that American cars are worse than everyone else for miles per gallon. Maybe not surprising. And so we can see there the difference. So the Japanese cars are slightly better. European cars are somewhere in between. And American cars tend to have the lowest miles per gallon. So there is a difference. And so it seems like there could be some predictive capability in that variable. Now, if these almost look the same, so if their means were very close to one another, I would say it's not very predictive. Maybe we shouldn't use it. So how do we use it? We need to turn it into something that the model can lock onto, because if we just put it in there as 1, 1, 2, 2, 2, 3, 3, 3, that to the model feels like 2s are more important than 1s. And that's not necessarily the case. And so what we're going to do instead is we're going to change that variable into multiple columns. And yes, that's called creating dummy variables. And so pandas can do this. There's a function in there called getDummies that will do that automatically. And it's almost like magic. It's so easy. You just say, here's a new data frame. We're going to do getDummies on the origin name column. We're going to the prefix is origin, and we're going to set its data type as int. And what it's going to do is give us back something that has a 1 if we're that particular origin, and it has a 0 if we're not. And so they also call this one-hot encoding, because for each of these new columns, only one of them is going to be set at a time. So one of them is set to 1, the rest will be set to 0s. And so basically we created new variables that each of which represents just a true or false value. And so when we do that, I've randomly sampled some values out of the data frame, or well, not randomly, I picked some specific values out of the data frame so we can see 2 American cars, 2 European cars, and 2 Japanese cars. And we can see the way the ones and zeros look. And now we have this new data frame that has these new variables. And so I'm going to add those 3 column names: origin American, origin European, origin Japanese. Add that to my random variable columns in the next cell. And so I'm going to run that. And then I'm going to evaluate my models. Now, I want to do this a bunch of times, but there's no need for me to keep rewriting the code. So I wrote a little function that's going to do cross-validation and then print out the R-squared and the MAE. And so I'm going to run that just to put that function into memory. And then I'm going to reevaluate the linear regression model, the quadratic model, and the random forest model, just so we can compare. And that result happens pretty quickly. So without versus with origin info, well, it added a little bit of performance for the most part. So it added a tiny bit of performance, but to be honest, it's not that much better. Right? So the R-squared went up in almost every case, I think. Let's see. Actually, it's interesting with the polynomial model, it actually went down slightly, but it's within the standard deviation. So it made almost no difference. And with the random forest, again, we're well within standard deviation, and the MAE didn't change. And so it made almost no difference. That's not always the case. Sometimes you put a categorical variable in there and your performance would be much, much better. And so this particular example, it didn't show much improvement. And so maybe it wasn't worth the trouble. But again, in your particular problem, you can use the same technique and it might make a big difference. And so it's worth knowing how to do that. By the way, there's more than one way to do it. So pandas can do it through that get dummies method call here. But scikit-learn also has a way of doing it that you can do in a data pipeline, like a transformation, and they call it one-hot encoder. And so if you wanted to look that up, you can look up one-hot encoder from the sklearn documentation. That's normally the one that I use. I've only recently started using the pandas way of doing it, the get dummies thing, because usually I don't want to change my data frame. I just want to change it during my pipeline while I'm training. And so the one-hot encoder can do that for you. But either way, whatever you think is easier and nicer, do that. It's nice to have more than one way to do it. By the way, if you want to see about other ways of encoding categoricals, there's a link here to a Kaggle discussion that talks about lots of different ways of doing it. And so that's it for the tutorial. We actually used up more of the time than I thought. We had some good questions along the way. So in this last minute or so before they call us back in, open floor, any questions?
I don't have any questions right now, but I just want to say, like, thank you for this. It's been really insightful. You're a very great teacher. And I don't know if you have YouTube channel or something like that. Or...
I don't have a YouTube channel. Yeah, I don't have enough free time to create one actually. No, I don't have a YouTube channel, sorry. I think they will be posting these workshop videos though.
Okay, all right. Thank you.
Okay, I'm going to go ahead and stop the recording. So thank you all. I will stick around until they kick us out. So if you have further questions after we stop the recording, go ahead and stick around. But thank you all so much for joining.